Hi, my name is Bill Egan. I'm the System Road Foreman. I would like to take this opportunity to introduce you to Conrail's new state-of-the-art locomotive, the EMD SD-80 Mac, and also go over with you the revised EL-106 form, which all of you use when reporting locomotive defects. The EMD SD-80 Mac has been designed to provide the highest productivity of any locomotive available in the industry today. It is the most fuel-efficient locomotive of its kind, has all of the latest technology on board, and is designed to be easily maintained. It has been 18 months in the making, and Conrail has purchased 28 of these locomotives. After watching this video, I feel confident that you will agree the EMD SD-80 Mac will enhance the performance of our company and reinforce our commitment to you to ensure the safest possible working conditions. Please feel free to send any comments you may have concerning the new locomotive and the EL-106 to the address displayed at the end of your video.
The locomotive, symbol of a powerful industry and a growing country. It moved this nation. Although its purpose has remained unchanged for 165 years, the way it accomplished that purpose has been under continual change. Gradually increasing in size and power, the steam locomotive was king until the 1950s, when diesel-electric technology revolutionized locomotives. Today, new technology is again poised to revolutionize the locomotive: AC traction. During 1996, Conrail will be taking delivery of 28 of Electro-Motive Division's SD-80 MAC locomotives. The SD-80 MAC, or 80 Mac, is one of the most powerful and advanced locomotives available today. It is powered by an electronically fuel-injected 5,000 horsepower, 20-cylinder, 2-cycle diesel engine. The locomotive is equipped with an air-conditioned whisper cab, a desktop control stand with integrated cab electronic displays, and electronic air brake equipment. The most notable features of this new locomotive are the self-steering radial trucks and a new proven AC traction system. In this video, we'll show you some of the differences with this locomotive, comparing it with an SD-60i. We'll review some important safety considerations and cover the new features, performance characteristics, inspection, and troubleshooting procedures you need to be familiar with. Because of the greater capabilities of this locomotive, there are also some important train handling considerations we need to cover. So, let's take a look. Well, here it is, the latest and greatest from EMD. Aside from the new paint scheme, from this view, it looks pretty much like one of our SD-60i locomotives. But let's take a walk to the side and take a look. Now you can see some of the differences. First of all, the SD-80 Mac is longer than an SD-60. The 80 Mac is 80 feet long. The SD-60 is 72 feet long. The SD-80 Mac is the largest locomotive in our fleet. Here's another difference. The dynamic brake grids are right behind the cab on the SD-60i. They have been moved to the rear of the locomotive on the 80 Mac. This allows better airflow to the grids and moves a source of noise away from the crew cab, improving the quietness of the whisper cab. The 80 Mac has larger radiators than the SD-60 to accommodate the cooling needs of the 20-cylinder diesel engine. The fuel tank on the 80 Mac holds 5,800 gallons. The SD-60 holds 5,000 gallons. Both number 1 and number 2 main reservoirs are on the right side of the 80 Mac, while on the SD-60, the number 1 is on the left side and the number 2 is on the right side. Now, here's a major difference between the two locomotives: the trucks. The SD-60i is equipped with standard HTC trucks and 40-inch wheels. The SD-80 Mac is equipped with HTC R2 self-steering radial trucks and 45-inch wheels. One of the most revolutionary features of this new locomotive, this truck design greatly improves weight distribution to the axles. It also allows the front and rear axle to steer when in curves. This reduces wheel flange wear and greatly improves adhesion. Let's take a closer look. Again, we'll use our SD-60i comparison to highlight the advanced features of this truck. On the standard HTC trucks found on the SD-60, weight is transferred from the locomotive frame to the truck, through the center plate, to the truck bolster, and then to the truck frame and to the axles. Because the weight of the locomotive is concentrated on the center plate, when tractive force is applied to the truck, a weight transfer takes place, much like what happens to your car when you push hard on the accelerator. The front goes up and the back goes down. This tipping of the truck will shift the axle loads, putting more weight over the trailing axle and less weight over the leading axle. Since adhesion is directly dependent on weight over the axle, the lead axle is more susceptible to wheel slip than the other axles. This weight transfer is not something you can see on a locomotive truck, but it does take place, and it can cause a wheel slip problem on the lead axle of the truck when high power is applied. Now, let's take a look at the SD-80 Max HTC-R2 truck. The HTC-R2 doesn't have a center plate or a truck bolster. It's equipped with a center pivot pin, which is used to transfer tractive force and bears no real weight. The weight of the locomotive is transferred directly to the truck frame through 4 rubber compression springs. This spreads the weight more evenly throughout the truck and reduces weight transfer, which greatly improves adhesion. Another important feature of this truck, and a major difference from the SD-60i's HTC truck, is the HTC-R2's ability to steer or realign its axles in curves. Let's take a look. When an HTC truck enters a curve, because of its rigid axles, a high angle of attack exists between the wheels and the rail of the leading and trailing axles. This high angle of attack causes the wheels to have a greater tendency to slip and also produces greater lateral loading on the rails. When the HTC-R2 truck enters a curve, a self-steering mechanism within the truck realigns the leading and trailing axles with the curve. This produces a radial alignment of the axles, which reduces wheel and rail wear and also lowers rolling resistance. Now, here's something that's brand new. An electric motor-driven parking brake. No more handbrake. Mounted on the left side of the front truck is a small DC electric motor. It drives a screw jack that will apply or release the brake shoes on the left number 2 and number 3 wheels. The electric parking brake is operated using a switch located on the engine control panel inside the cab of the locomotive. In the event the locomotive is dead and battery current is not available, the parking brake can be applied manually on the ground by using a cranking tool, which will be stored on the locomotive. Another important feature housed on the trucks is the flange lubrication system. The systems are identical on the SD-60 and the SD-80 Mac. The flange lubrication system is designed to reduce curve resistance, saving fuel and reducing wheel flange and rail wear. This feature, working together with the radial truck, makes the SD-80 Mac one of the most fuel-efficient locomotives in our fleet. The HTC-R2 truck lacks the center plate, truck bolster, side bearings, pedestals, and pedestal liners found on older HTC trucks, but does have additional components, such as traction rods, steering beams, and steering linkage. These components are readily visible from the ground and should be inspected during the locomotive's daily inspection. Now let's take a look at one of the most important new advances of the SD-80 Mac, the AC traction system. With modern DC locomotives, like our SD-60i, the diesel engine is used to turn the main generator, which is actually an alternator producing AC current. This AC current is rectified, changed from AC to DC, at the main generator. The main generator's DC current output is then fed directly to the DC traction motors. With AC traction systems, we start out the same way. The diesel engine turns the main generator, AC current is rectified to DC. Now here comes the difference. The main generator's DC output is then fed to two computer-controlled inverters, one for each truck. The inverters convert the DC current back to AC, which is then fed to the AC traction motors. By controlling the voltage and frequency of the AC current, the inverters control the speed and power of the AC traction motors. Although AC motors have been around for a long time, until just recently, AC motors just couldn't match the starting torque of DC traction motors. Because of this, DC traction motors have been the choice since the early days of the diesel electric locomotives, right up to our SD-60i locomotives. Along with this high starting torque, DC motors brought along many limitations. DC traction motors are equipped with commutators and carbon brushes, which are subjected to very high current loads. Applying high current loads to a DC motor that is not turning or turning very slowly can cause severe damage to the commutator and the brushes if the high current is applied for too long a period of time. At the upper end of the locomotive's amp range, this can be just minutes. This is referred to as the short time ratings for the locomotive's traction motors. AC motors are not equipped with commutators and brushes, so AC traction motors do not have this limitation. That means no short time ratings. And now, because of advances in computer and inverter technology, the starting torque of the SD-80 Mac's AC traction motors actually exceeds its older DC counterparts. The nature of these AC traction motors also makes them less susceptible to wheel slip. DC traction motors also require high current levels or amps to produce high power. Heavy traction motor leads and conductors must be used to carry that high current, and the high current also produces a great deal of heat, which further limits the DC traction motor. The SD-80 Mac's AC traction motors rely more on the frequency of the alternating current to produce power. For that reason, you will not find an ammeter on the control stand display. Instead, the locomotive's computer system calculates and displays tractive effort in pounds on the cab display for each AC locomotive. Tractive effort is the actual force the locomotive, less its own rolling resistance, exerts at its coupler. Now the engineer can get an actual indication of how much pulling power he is applying to the train. This is a great feature. Let's go up and take a look in the engine room. But before we do that, there are some important safety considerations with AC locomotives we need to review. Unlike the high voltage circuits found on conventional DC locomotives, the AC traction system found on the SD-80 Mac and all AC locomotives requires components to store energy in the form of high voltage. These high voltage circuit components are referred to as DC-link capacitors and are capable of storing a charge of 3600 volts DC. This high voltage can be present in the high voltage or traction control cabinet of the locomotive even when the locomotive is shut down. The high voltage traction control cabinet on the SD-80 Mac is located just behind the cab with access from the running boards. Only qualified maintenance personnel are allowed to access this area of the locomotive. For the purpose of protecting personnel and equipment, this locomotive is equipped with 3 automatic discharge systems which will reduce DC link capacitor voltage to 0. The first system functions whenever the reverser handle is moved into the neutral position. Bleeder resistors will bleed off the capacitors to 0 volts. The second system will discharge the capacitors through the dynamic brake resistor grids anytime the isolation switch is placed in the isolate position. The battery switch must be closed and battery voltage must be present for this to take place. The third system will discharge the capacitors whenever the diesel engine shuts down. When the diesel engine shuts down, the auxiliary generator ceases to produce output. The inverters require auxiliary generator output to function properly. So when auxiliary generator output is lost, the inverter triggers a protective electrical crowbar. This electrical crowbar creates what is essentially a direct short circuit across the capacitors, which discharges them instantly. To be certain that the automatic discharge methods have functioned properly, a system self-test can be executed using the control stand display. If the self-test determines that voltage has not been removed, the user will be notified by computer display messages and the sounding of an alarm. Let's go take a look in the engine room. We'll start on the left side, work around the locomotive, and then right up into the cab. Just behind the cab is the high voltage traction control cabinet. This is where the capacitors, inverters, and high voltage switchgear are housed. Again, only qualified maintenance personnel are authorized to access this area of the locomotive. Moving back, in this area, the main generator, turbocharger, and turbocharger aftercoolers are located. This is referred to as the generator end of the diesel engine. The main generator is connected directly to the crankshaft of the diesel engine, which is housed in this area of the locomotive. This 20-cylinder, 2-cycle, 710 diesel engine is the heart of this powerful locomotive, pumping out 5,000 horsepower. The basic construction of this diesel engine is the same as you would find on all EMD locomotives. On the top of the diesel engine is the exhaust manifold. Below that is the top deck area, the cylinder test cocks, airbox covers, and crankcase covers. And of course, the lube oil dipstick for checking the lube oil level of the diesel engine. Moving back, we are now at the accessory or free end of the diesel engine. This is where the water pumps, oil pump, and electronic fuel injection components are located. Notice there is no governor. It has been replaced by the electronic fuel injection components. Engine water fill and the water level gauge are accessible from this area. Further back is the water expansion tank, the fuel oil filters, and below the fuel pump and lube oil filters. These next doors access the AC cabinet, which houses the electrical components for the electric motor-driven equipment and traction motor blowers, the radiator fans, and the electric motor-driven air compressor. This cabinet contains high voltage. This area at the rear of the locomotive is where the dynamic brake grids are located. Moving around to the right side of the locomotive, these doors access the electrically driven 4-cylinder air compressor. Inside, there's a dipstick to check air compressor oil level that should be checked whenever the diesel engine lube oil is checked. Behind the next doors, the lube oil cooler is located, as well as the air supply cutout cocks for the horn, split cooling system valve, and the air start magnet valves. And now we are at the right side of the accessory or free end of the diesel engine. Here you will find the crankcase pressure reset. This is the only manually operated reset found in the engine room. Other diesel engine protective devices are reset automatically or can be reset using the display on the engineer's control stand. These include protective devices such as engine overspeed, low water pressure, and low oil pressure devices. Like all other EMD locomotives, the engine water fill, water level gauge, and main water drains are accessible from this area. Further up, we have all the same components we saw on the left side. And now here's something you won't find on other EMDs, the air start motors. Because of the size of this diesel engine, the electric starting motors may need a little help turning over the engine during starts. Two air-operated motors provide that help. You need about 80 psi of main reservoir pressure to operate these motors. Eventually, EMD plans to replace this system with one that utilizes the companion alternator to start the diesel engine.